G'day chemistry students, in this video we are again looking at dot point 8.2.2. Our focus is on NMR spectroscopy and how this spectroscopy technique actually works. Let's get into it. Now the first concept that I'm going to introduce is this idea of nuclear spins. It's a property of atoms and really delves into an area of physics and chemistry, or more specifically physical chemistry, which we don't need to know a lot about in detail. To explain how NMR works, I will need to refer to it though. So generally speaking, when we're talking about a nuclear spin, we're referring to the behavior of nuclei in an atom. And we do use this word spin. If you wish to visualize a spin literally as a round sphere spinning in one direction or the other, you're more than welcome to. I will say technically though, this is not the behavior that we are actually talking about when we refer to nuclear spin itself. Why nuclear spin can be really helpful is we can use this concept of spin to start talking about direction. So these spins for a nuclei can be pointing in any direction, but in the presence of a magnetic field, what we can have happen is that the nuclei can either go with the direction of the magnetic field or go against the direction of the magnetic field. So in the presence of a magnetic field, what we can see is that the spins of nuclei are either aligned with or against the direction of the magnetic field. However, the nuclei have this resonant frequency, very similar to what we were talking about with IR. But instead of having bonds vibrate by differing amounts, what we see instead with the resonance is that the nuclei can absorb radio waves and actually have a magnetic spin flip. So what we see here is that at the ground state, we have a bunch of different nuclei all pointing in that upward spin direction. We have a bunch of nuclei all pointing down for their spin direction. The up spins have lower energy and the down spins have some higher energy. But if we were to introduce some radio waves, one of these ground state or lower energy nuclei can have a spin flip. And so instead of pointing up, it will now point down, meaning that it has absorbed some energy and as a result has flipped its magnetic spin. Now this happens with odd numbered isotopes. So in particular for us, when looking at organic chemistry, the best ones to analyze are H1 and C13 atoms. They're the best ones to look at. So when we're doing NMR, or again, nuclear magnetic resonance, what we need to do first is have our sample sitting in an electromagnet. That will mean that all the nuclei will set their spins in place, but there won't just be a magnetic field that's present. What we can also have is a radio frequency generator, which will generate different radio waves that will cause these spin flips to happen. And then we can use a radio frequency detector to figure out where some of those radio waves were absorbed. Similar to IR, if there was any radio waves that were absorbed, that means that we found a resonant frequency. And at those resonant frequencies, that's where we're getting this spin flip in nuclei. Now, the reason why we have different resonant frequencies is because of this idea of electron shielding. So generally speaking, in an organic molecule, all nuclei will have some amount of electron density around it. The more electron density that there is, the more that those electrons are going to be actually interfering or shielding the nucleus from experiencing a magnetic field. So for example, if there is low electron density, then the nucleus is actually going to experience a stronger magnetic field. And that's because there isn't a lot of density of electrons there to shield, again, the nucleus from the magnetic field that's present. Conversely to that though, if we have lots and lots and lots of electron density crowding the nucleus itself, that's going to mean that any incoming magnetic field, a lot of it's going to be blocked and deflected, and only a little bit's going to be able to actually get through and hit the nucleus. As a result, what we will see is that the nucleus experiences a weaker magnetic field. And so if some nuclei are going to be experiencing strong magnetic fields and some are going to be experiencing weak magnetic fields, these flips that we observe are going to require different amounts of radio wave energy. So for example, if we have a nucleus that experiences a strong magnetic field because there's not a lot of shielding happening, you're going to need a high energy radio wave to flip the influence of the magnetic field. Conversely, if we have a nuclei that has really high electron density that's blocking a lot of the magnetic field from the electromagnet, there's going to be a weaker magnetic field that's being experienced, meaning that you won't need a high energy radio wave, but instead can just use a low energy radio wave to actually flip that nucleus. And as a result, we end up with an NMR spectra that might look something like this. Our 0 point is kind of a reference point. So usually we do like a reference or a zeroing or a calibration by using TMS, which is tetramethylsilane. And this molecule has extremely high shielding. The reason being that all of these bonds on the hydrogen are extremely non-polar, including the bond between the carbon and the silicon are extremely non-polar bonds as well. What that means is that electron density isn't being pulled away from any of the hydrogens and instead are being shared very evenly amongst all of the particles. Hydrogen itself, especially when we're talking about polar bonds, very used to having its electron density pulled away from it. As a result, this we can say would be the highest electron shielding that we would expect hydrogen to see on any organic molecule, which means if it's highly shielded, it's going to require the lowest amount of radio energy to actually get that flip to occur. Furthermore, because this molecule has 12 hydrogens that are pretty much all the same, it's a very symmetrical kind of molecule, it produces a really large signal that's very easy for the NMR machine to detect. What that means is as we go across from this 0 point, and notice that we do go from right to left, we end up getting lower electron density. And that's because there is higher degrees of polarity between bonds, which is pulling away that electron density from the hydrogen. This means that there's less shielding. And as a result, because there's less shielding around those hydrogens, there's going to be a stronger magnetic field. And as such, if there's a stronger magnetic field, you will need a higher energy radio wave to actually get, again, that nuclear flip to happen. Technically, this is the spectra for hydrogen NMR, and TMS is used to calibrate hydrogen NMR spectra. Similar principles are used in carbon-13 NMR as well. So if we're looking at a HNMR spectra, what we'll see is over this side away from the 0, we're looking at hydrogens that are bonded or very close to polar bonds, which pull away that electron density, again meaning that a stronger or higher energy radio wave is required to get that nuclear flip to happen. All of the ones that are over this way, generally speaking, are surrounded by non-polar bonds, meaning that there is a lot more electron density on those hydrogens, meaning that they are a lot closer to our 0 value. For carbon-13, there's actually a list of shifts in your data sheet, measurements of how far away they are from 0. You'll notice that the scale's a little bit different too. We go all the way up to 220 on our carbon NMR and only up to about 10 to 12 on HNMR. Just some differences in the energy requirements for carbon versus hydrogen, not something that you have to be concerned about too much because they're two completely different spectra and graphs. But when you are looking at the peaks and the shifts on carbon NMR in particular, you'll see as well that the smaller shifts are generally caused by non-polar conditions and the largest shifts are generally caused by polar conditions. But this is not always the case either. The general idea is when you're using one of these NMR that you're using the shift data and matching the peaks to what you see. What I will note as well is that there are some differences in resolution. For carbon NMR, most of the time you will just see lines that are matched to or associated to these chemical shifts, whereas in HNMR, we can see much more detailed sets of peaks, and in particular, you may even see some of these what we call splitting patterns for each of the sets of peaks. I'm going to talk about what these splitting patterns are and how they work in the next video, but the reason why this is the case all comes down to the abundance of carbon-13 and hydrogen. So for carbon-13, when we're actually analyzing the carbons on organic molecules, we only actually get resonance here for about 1% of the carbons present in the sample. As a result, the strength of the signal that we get for any of these carbons, not particularly high because there aren't that many carbons in the sample to be generating any kind of signal. As a result, the detail that we get from our measurements is quite limited. and that leads to us just getting single peaks. In comparison though, when we look at HNMR, pretty much all of the hydrogens are hydrogen 1, meaning that every hydrogen on our organic molecules in our sample are helping to produce a signal, because pretty much all of them are resonating with our radio frequency. And as a result, that gives us a higher resolution spectra that's a little bit more detailed. And we can actually use this detail to our advantage when I teach you how to use our HNMR spectra in the following video. Thank you very much, everyone. In the next video, I will show you again how to use and interpret HNMR and CNMR spectroscopy. The applications that we have are slightly different, and again, that comes down to the resolution of each of those spectra, but we'll have a look at that in the next video.